Hello guys, welcome back to this new video. Today I would like to make something a bit special. So I was browsing the marketplace, second-hand marketplace in China a few days ago, and I came across this very cute keyboard. And it's weird, but like I was checking online and I couldn't find any information about it, or very few informations. So this is made by Alcatel. It seems like this keyboard was meant to be connected to a phone like the OT715. So as you can see, the prices were quite low. It's around $2 or $3 US. So I decided to buy one, and today it arrived. And actually, I bought two of them. So the goal would be to try to understand how this works. Since I don't have any technical specification or any manual, I couldn't find technical stuff about it. We will try to reverse engineer it, try to understand how it works, try to then interface it with something else, and maybe, ideally, in the end, try to connect it to a Zeal 8-bit computer. Let's check if everything is okay. Okay, it's nice. I expected it to be a bit smaller. Okay, it's quite dirty though. This looks... I don't know if you can see it on camera. Yeah. This looks like a 2.5 millimeter connector. I can try to measure it. Yeah, 2.5 millimeter, or yeah, 0.1 inch. I suspect this one is ground. This one may be VCC, maybe 3.3 volt. This may be RX, TX in the simplest case, if it's using some serial protocol. I can try to disassemble it and check what's inside. Here. Okay, I was able to remove it. It looks very fragile actually, like those cables connected like that. That looks very fragile, to be honest. There's not that many things going on the board. All those vias are connected to the keys that are on the other side. Maybe it's two-layer board. Yes. Okay, let me turn that around. That looks very clean. So we have a chip. What is this? This is W78LE52F24. Maybe it's an MCU. I would say it's an MCU. Then we have a lot of resistors, capacitors. 80. This chip is 8000. I suspect maybe it's for power, maybe power, then some transistors. Okay, I'm going to check online what this chip is. So this is a voltage regulator that can be adjustable. This is the this is the IRU1205. Here it's adjusted with two resistors, which I think are this one and this one. I have to check. Here we have an MCU, as I was expected to. This is an 8-bit MCU, I think, so it has internal ROM, internal RAM, and it supports from 2.5 volts up to 5.5 volts. There's something I did not notice before, but there is only 3 pins here. So which means that on our cable there is one of them which is not connected or bridged to another one. I check the left one first. Okay, so the left one is the sleeve. I check it's not connected to other ones. Okay, then we have the middle one. Okay, so the middle one is connected to the 2 in the middle. Okay, and then we have the right one, which is connected, yeah, to the top, to the tip. Okay, so the middle one is connected to the 2 sections that are in the middle of our connector. So I suspect this is ground, and we can check. Since I found the data sheet for the voltage regulator, the pin that is in the middle is ground. So this one should be ground. And if I connect, yeah, okay, so this is ground. This is ground. This may be voltage input. We can try. Voltage input is pin number 1, which is this one. Oh, it's not connected. Oh, okay, so this is voltage input. So voltage input in this one is this one. So this one we said it's the tip. So this is voltage in. This is ground, both are ground, and this is data, I guess. Yeah, I should check where this goes, but anyway. So I've just taken out the microscope to check better. So indeed, in the middle is the ground. We can see there is a huge plane here. So the right one seems to be voltage input. And we can see that it goes to the big capacitor and then to the voltage regulator. Here we have V out. So voltage output, we can see that it goes to here, then here, and to the VCC pin of this microcontroller. Okay. So this is V out. This is a adjust pin of the voltage regulator. We can see a 38 ohm resistor between them. This has no marking, unfortunately, and when I test with my multimeter, it's around 250 kilo ohm. I think the simplest thing to do now will be to connect those wires directly and try to probe them to see what will happen. Okay, I'm back with the camera. I think what I'm going to do now is directly connect voltage input, ground, and I will probe the output. I'm going to have a try to provide 3.3 volts first, even though the voltage regulator supports more, and if it works, if I see something on the data line, then I'm going to try with 5 volts. Maybe I should also close this because they are the keys, or at least put it like this. Let's have a try with some connectors. For the 3.3 volt, I'm going to use, okay, I have an ESP32 lying around. It has 3.3 volt regulator on it, so I'm going to use this. Yep. I'm going to break some cables. I just brought my breadboard. I connected a few cables. So the black one is ground, it's GND. The yellow one is power voltage input and not data. Data is the red one. Okay, I connected everything. I can plug the USB cable to the USB board. Board is powered on. Let's check the voltages. Let's check the voltages here. 3.3 volts, great. Now we have to check V out. 2.4 volts, okay. So the voltage regulator applies outputs 2.4, 2.5 volts to the MCU, which is the minimum allowed voltage for the MCU. It's okay, now I can probe maybe the data line. I have my oscilloscope. Yep, seems to be serial protocol. Great, awesome. Okay, so now that I understand how it works, there is just one thing I would like to do. I would like to try the 5 volts before closing the case and everything. Let's have a try. Now I'm going to plug it to 5 volts. Okay, let's have a try. We have 4.7 volts. And what about the output? 2.4 volts out on the output of the voltage regulator. We may want to check the 2 volt. Okay, so the output of the UART, the output of the serial pin is still 2 volts. Okay, so I'm going to close the case and then maybe bring the logic analyzer, which will help us maybe a bit more. Let's do this. Now I need to connect it to my logic analyzer. I'm still going to use the SP32 for power, but then I will not connect it to the oscilloscope, but my logic analyzer. Let's do this. Okay, I connected the data pin and ground to the logic analyzer, the power to the ESP32. I'm going to open the logic analyzer. Let's listen. Oh. Okay, there is a lot of noise. Okay, there is a lot of noise on the data line. So did I plug the... Wait. Threshold level. Let's put this threshold to 1 instead. Yeah, okay, that's much better. Space. Since the high level was 2 volts, having a threshold of 1.7 is way too high. Okay, so it detected 2 presses. Let's try to decode this into UART. Baud rate, huh? Okay, so I think I found something. So if I press 1, 2, 3 keys, I get 6 data. So which means that there is a key press and a key release. That's my guess, at least. But then I'm not sure about the baud rate. So here I'm currently using the baud 200 and it looks correct, but here I'm not very satisfied with what I'm seeing. Here we can see, so the dot is where the data was sampled, and we can see that this one is missing, and here it's sampled at the end. So maybe this is not the right baud rate. So I noticed that how fast is this change? This state lasts for 831 microseconds. So what happens when we divide 1 by 831 microsecond, of course, and we get something about 1200. So I change the baud rate to 1200, and now I get something much better. We have B1, and I suspect this is just like a very big start bit or something to tell the phone or the device that it was connected to that, hey, I'm going to send some data, so get ready. Maybe like to trigger an interrupt or something like this. Because every time we have a key that is pressed or released, we have this very big start bit. And here it starts being correct. So here we have B1 for the key pressed. Bit 7 should be set. And key release, bit 7 is 0. So bit 7 here is cleared. And the data is 31. And it's great because 31 is the ASCII code for 1, for character 1. And we can check this. We can use ASCII instead. And yes, it's 1. So if I press, let's see if it works for the characters now. Q, W, E, R, T, Y. Key pressed, key release is a Q. W, E, yeah, so it works. So it's using ASCII. It's using ASCII for the key release, and for the key press there is just bit 7 that is set. But what about special characters? Let's have a try. I'm curious about Alt Maj, maybe, if I press A at the same time. OK. Oh, I think I pressed too many keys. I don't recall what I pressed. 8F, so it will be F, yeah, okay. Here we have 8E, so there is no key release for this one. Or is it because, oh, because I pressed it at the same time with A? Oh yes, so this is A, so the character that was before 8E should be the uppercase, the shift, sorry, it should be the shift. Then here we have 0E. Okay, that looks pretty good. I just have to probe all the characters to guess what they all do. So now I understand how this protocol works. So it's using serial protocol, but with a very big start bit before any transaction, and it's separated by 10 milliseconds, 10.2 milliseconds. And the baud rate is 1200. Okay, that's pretty slow. That's quite slow, but considering that this keyboard was supposed to work with the very old phones, maybe from 2002, 2003, it actually makes sense now. Okay, so what is the next step? I think the next step is to make somehow a better PCB, something much better than just cables lying around, and then connect it to the Zeal 8-bit computer so that we can simulate the same protocol via GPIOs and just detect which characters are being pressed. So I think that's it for this episode. We've already seen how this thing was made, what protocol it was using, and in the next episode we are going to try to connect it to the Zeal 8-bit computer and write a small driver to detect all the characters that are typed on the keyboard and maybe show them on screen. Thank you if you are still here up to now, and see you next time.